Hello.
Hello. Yes, we can hear you.
Oh, and you can see my screen?
Yes.
Yeah, give me a second to just, well, so I think it's all good. 1 second, please. Well, hello everyone. Good afternoon from this side of the world. I would like to thank the organizers for giving me the opportunity to present in this platform. My name is Golam Morshed. I'm a PhD candidate at the University of Virginia, and I will be talking about a recent work on pulse-activated probabilistic switching of medium barrier magnet-based perpendicular magnetic tunnel junction that can be used for building true random number generators. So random number generators are of great interest for various applications like cryptography, neuromorphic computing, Monte Carlo simulation, and probabilistic and stochastic computing, and many more. So the traditional random numbers are basically pseudo-random numbers that are produced from computer-based algorithm, but these pseudo-random numbers are not suitable for applications like cryptography or stochastic computing because the random bits are correlated to each other and it's kind of predetermined if you know the initial seed. And also it takes longer time, like in microsecond range, to generate the pseudo-random numbers. So we actually require true random number generator, and CMOS-based true random number generators actually use physical phenomena like thermal jitter to produce the random numbers. But here's the limitation: is it requires many transistors, like hundreds of transistors, which actually not beneficial both in terms of energy and area requirement. So on the other hand, magnetic devices based random number generators are true random number generators, and it costs only a little energy, like in the femtojoule range, and also the area is not that much high, and the throughput is high for this type of true random number generators. And they also passed all the niche tests to qualify it as a true random number generator. So one of the fundamental building block for spintronic true random number generator is this magnetic tunnel junctions. So magnetic tunnel junction is a multi-layer structure where an insulator is sandwiched between two ferromagnetic layers. So one ferromagnet has a fixed magnetization direction, which is called this pinned layer or the fixed layer. And the other ferromagnet can actually reorient its magnetization depending on an external current or voltage using this well-known effect spin transfer torque. So depending on the relative orientation of these two magnetic layers, we can actually get two resistance state, which is parallel and anti-parallel, and that can be used for storing data. And as well as for stochastic switching, we can actually use this behavior to create random number generation. And this free layer of this MTJ has these two separate state, and that is basically separated by an energy barrier EB that basically comes from the anisotropy. And depending on the value of this energy barrier, we can actually categorize this free layer as high barrier magnet, low barrier magnet, and medium barrier magnet. So for the case of high barrier magnet based true RNG, here the energy barrier is greater than 40 kT. So it has this limitation that you require large current, which is not energy efficient, and also the throughput is low. And recently, this low barrier magnet based MTJ, which is known as super paramagnetic tunnel junction, where the energy barrier is close to the thermal energy. So without any external stimulation, the magnetization can actually flip from one state to the other. That basically gives rise to this stochastic behavior that can be used for true random number generation application. But here the problem is, like, the dynamics is very slow because there is no like external stimulation, and also it's sensitive to process variation. And most importantly, these are very hard to fabricate. So the next category is the medium barrier magnet, which is the focus of my talk. And I hope I can convince you throughout the talk that MBM activated with a short pulse can actually be used as a fast, low energy cost and robust source for true random number generator. So for a magnet driven by a current with the presence of thermal energy the magnetization dynamics can actually be described by the stochastic LLG equation. However, there is another approach called Fokker-Planck equation. Here, this is an alternative and efficient way to estimate the probability of switching. So in case of the stochastic LLG, we actually keep track the magnetization and we do a large number of sample, let's say 1 million, and from there we can get the probability distribution. But in the case of Fokker-Planck, we can actually get the probability density in one shot, and from there we can actually get the probability of switching. And here this parameter D is basically taking into account the effect of thermal fluctuations. So here we use 35 kT energy barrier magnet that is activated by a short pulse, like for example here I'm showing a 1 nanosecond pulse, and we actually tune the magnitude of this pulse in such a way so that we can get the probability of switching as 50%, which is required for this random number generation application. So here in the bottom left, you can see the probability density. So we started with a initial probability density that is like a Boltzmann distribution. So all the probability is like concentrated around this theta equal to 0 well, which is basically the North Pole. And we relax the system for a couple of nanoseconds, and you see the probability distribution changes only a very little because of the thermal energy. And once the pulsing is done, and right after the pulse, you see the probability has already shifted to the other end, which is theta equal to pi, and related to this South Pole. And if we relax the system for a couple of more nanoseconds, we can actually get this clear bimodal distribution that can actually give like 50% probability of switching. And this evaluation of this PDF during the pulsing can also be seen from this color plot. Here you see at the initiation of the pulsing, the PDF was concentrated in this North Pole, and then it started like moving towards the other pole, which is the South Pole. And this is the probability of switching phase space as a function of pulse amplitude and pulse duration. And this blue overlaid curve is basically the 50% probability regime that is basically required for true RNG application. And you see this pulse amplitude and pulse duration has kind of an inverse relationship, which is expected. And if we decompose this heat map to the individual component, you can see how the probability of switching changes as a function of pulse amplitude and pulse duration. And here you can see our numerical Fokker-Planck data are basically matched with the stochastic LLG data that is done by Professor Shalu Rakheza's group at UIUC. And we also matched our Fokker-Planck data with the experiment from Professor Andy Kent's group at New York University. And here we see our data agrees very well with the medium barrier magnet-based experimental data of 40 kT magnet. And now we talk about the important metric, which is basically the energy consumption in the switching process. And here you see the energy consumption as a function of pulse amplitude and pulse duration. And here it is clear that the energy required for this type of switching is low in the order of femtojoule. And we also calculated the energy delay product. And this has kind of opposite trend as a function of pulse amplitude and pulse duration. But from this figure, we can conjecture that this optimal value for this low energy switching is around the 0.5 volt, and then the optimal pulse duration is less than 1 nanosecond, which is this short pulse regime known as the ballistic switching. Now, one of the important factor is this robustness or reliability of this 50% switching regime. And there are like a couple of parameters. One thing that is needed is basically this voltage that required for this 50% probability of switching, which we denote as like VHAV. And here you see we show that VHAV for a wide range of pulse duration. So in practice, this is not like feasible. You pin down the voltage in such a way that you will get 50% all the time. So we need to take account the impact of the variation of this VHAV. And in the right figure, you see when we plot the VHAV for this low short duration pulse regime, the change in 50% probability of switching is lower than the longer pulse regime. So that basically represents the robustness against this voltage variation. And the other important parameter is the temperature. So the temperature has effect in the initial probability distribution and also the thermal stability factor of the free layer. And as you can see, when the temperature increases, the delta value basically decreases. That means for a specific VHAP and pulse duration, you will get a higher probability than 50%. And when the temperature decreases, it is the opposite case. So here we find this P switch has a linear relationship with the temperature. And from here, we can basically extract the slope that basically gives us a change of this 50% probability with respect to temperature. And again, we see for this short pulse regime, the DPDT value is lower than the longer pulse regime. And also, it is interesting that the focal plane data are matched with this macrospin approximation in the short pulse regime. And our focal plane data also matched with the experimental data from Professor Andy Kent's group again, which is very encouraging. And finally, we want to see the impact of various geometric and material parameters on this 50% switching probability. So we vary like the free layer diameter, thickness, and saturation magnetization, damping, and other parameters. And these are basically kind of changes the parameters that actually control the switching characteristics. So from this figure, you can see like overall for all these variations in the short pulse regime, the change of 50% probability is lower for every case than the longer pulse regime, which basically represents again the robustness of this type of switching for this process variations. So with that, I would like to conclude. So the take-home message would be is this medium barrier magnet activated with a very short pulse can be actually utilized for a faster, energy efficient, and robust PRNG unit for application like optimization problems, cryptography, and many more. So I would like to thank my professor, advisor Professor Avi Ghosh, and the collaborators from NYU, VCU, and UAUC for their contribution in this project. And I would also like to acknowledge the financial support from the funding agencies. So thank you very much for your patience. I would be happy to take questions. Thank you.
All right. Thank you, Golam. Please feel free to ask if you have any questions, or you can also put them in the chat box. All right, so I don't see any questions. So, Golam, you did a great job.
Yeah, thanks, Vaibhav. Yeah.